All right, good morning. I've been working all night while you've been asleep on this talk. So the title you just heard, and thank you for the invitation to speak. So here is the outline. So let me begin with some preliminary remarks. I'll be talking about a paper I wrote about a year ago with Dan Fried and Konstantin Telemann. And so the goal of this talk is to help you be able to read this paper. For those who are trying to read it, I should note that version 3 from last spring is a significant upgrade, and there's still some boo-boos and reference problems, so there's going to be at least a V4. The ideas in this paper and in this talk have many, many antecedents. Since I only have an hour, I'm going to skip over that discussion. The only thing I'll say is that what we add to all these antecedents is a systematic calculus of for computing with defects in topological field theory, especially in something called finite homotopy theories. And we explain how these theories allow us to implement symmetries, internal symmetries. Now, there are previous talks on this subject. There's a very nice series of pedagogical lectures that Dan Fried gave at the Perimeter Institute, together with pedagogical lecture notes in June 2022, and he gave a number of talks thereafter. And these are all online. And Konstantin also gave a very beautiful talk at the KITP last March. So let's begin with what I like to call fields without fields. If John Wheeler were with us today, he would call this topic of topological field theory fields without fields. So I need to say a few preliminary remarks about N categories. So I'm going to assume you know what a category is. If you don't know what a category is, you should probably give this talk a miss. A two category, an ordinary category is what's called a one category in this language. A two category then is a category in the usual sense where the Hom sets, Hom from x1 to x2 between two objects x1 and x2 are themselves categories. So for every pair of objects, x1, x2, Hom x1, x2 is itself a category. Now, the objects of that category, Hom x1, x2, are called one morphisms in C. The morphisms in that category are called two morphisms in C. And so it's logical to call the objects, x1 and x2, zero morphisms in C. And then we can compose these morphisms in various different ways. And so there are lots of compatibility conditions I'm not going to write out. But that gives you some sense of what a two category is like. And then an N category is simply a category C whose morphism spaces are N-1 categories. A very good example of an N category is the unoriented Bordism category of manifolds with corners of dimension less than or equal to N. So here, the objects, or the zero morphisms, are zero-dimensional manifolds. For example, a point, or perhaps a disjoint union of points or several points. The one morphisms then would be one-dimensional Bordisms between these zero manifolds. So the arrows here indicate not orientation, but what's ingoing and what's outgoing. And so here I've pictured on the left one of the one morphisms in our category, and on the right, another one of the one morphisms. No one said they had to be connected. So then a two morphism would be a manifold with corners, which is a Bordism between these one morphisms, and so on. Now, our N categories need a little bit of extra structure. They have to be what's called monoidal, and monoidal means there's a notion of product, usually denoted tensor product, on all the K morphisms. And if you have a notion of product, there should be a notion of unit, and the monoidal unit is denoted 1 sub C. So for the Bordism category, the tensor product is just disjoint union of Bordisms, and the monoidal unit is just the empty zero manifold. So an example of a monoidal category is the one category vect of finite dimensional complex vector spaces. Usual tensor product is the monoidal structure. The unit is the one-dimensional complex vector space. A good example of a two-category is to look inside the vector spaces, the set of all vector spaces, and choose the algebras, those vector spaces which admit an algebra structure, and choose an algebra structure. And so that gives you a two-category. The zeromorphisms are the algebras, complex finite dimensional algebras, and then a one morphism between two algebras is just a bimodule. This is my definition. And then the two morphisms between bimodules are bimodule maps. And the tensor product is the usual product, tensor product of algebras, bimodules, and so on. And the tensor unit is just the one-dimensional complex algebra. There's another two category that we're going to use a lot, which is the two category of categories. We can restrict our attention to suitable kinds of categories. The two category of categories has zero objects, zeromorphisms, which are themselves categories. The one morphisms are functors between categories, and the two morphisms are natural transformations between functors. Now here, it's not so obvious what your monoidal structure is, and you can define that, and that goes with names like Deline and Kelly and many others. So it's not a trivial thing. With the categories we'll consider, the set of categories we'll consider, the tensor unit will be the one category of vector spaces, vect. So now when we're doing fields without fields, what we do is we generalize the functorial picture of field theory going back to the work of Atiyah and Siegel. And the modern definition is that a p-dimensional field theory is a monoidal functor from this Bordism category, P category, of manifolds of dimension less than or equal to P to C, where C is some other monoidal P category. And then the idea is that the values of the functor on M sub K, where M sub K is a K manifold without boundary, compact K manifold without boundary, these values are the result, the answer, the result of doing the path integral. So we never see the fields that we do the path integral over. We just get the answer. And what the categorical language does for you is it formalizes the constraints of locality. Now, for suitable types of P category, then if M sub P is a P-dimensional compact manifold without boundary, the value of the functor on M sub P is a complex number, and that's called the partition function on M sub P. If N sub P minus 1 is a P minus 1 dimensional compact manifold without boundary, then the value of the functor on N sub P minus 1 is an object in the category of vector spaces. In other words, it's a vector space. It's called the state space on the spatial slice N sub P minus 1. If we go down to higher codimension, then F on such manifolds is a more complicated thing. It's an object in a higher category. One way of thinking about these is to think about defects within defects. So if I have a collection of theories, say, labeled by capital Latin letters like A, B, and C, so if I fill my space-time with a theory A, then if I have two different theories, I could imagine a domain wall labeled in green here between two theories, A and B. But there might be many different kinds of domain walls. So then we would have to label the different domain walls, and maybe we would call one domain wall P, but maybe there's another domain wall Q. And so those domain walls would have to be separated by some subdomain wall, higher codimension. But there might be many subdomain walls between P and Q, so they have their own labels, like alpha, and there might be many subdomain walls, and they would have domain walls within domain walls. So this is one way of thinking heuristically about the field, about the physical meaning of these Bordisms and morphisms and morphisms between morphisms and so on. Now, although I said we're doing fields without fields, we can add in fields so long as we remember that they're background fields. The fields should be locally defined on P manifolds. They should pull back under local diffeomorphisms and satisfy a sheaf property. So good examples of fields are orientations, spin and pin structures, G-bundles with connections, Riemannian metrics, differential cochains, perhaps foliations. And Freed and Hopkins formalized this notion. And if you have a field, a set of background fields denoted curly F, then you can modify the Bordism category to include Bordisms equipped with these structures. For example, so far we were talking about unoriented Bordisms, but orientation is a field. And so we could modify our Bordisms to oriented Bordisms or spin Bordisms or Bordisms with a G-bundle with connection and so on. And so a more general notion of what is a field theory is that it's a monoidal functor of these kinds of Bordism categories equipped with background fields to some P category C, monoidal P category C. So what's examples of these theories? Well, very good example are the finite homotopy theories. They're good because they're very computable. They're an important class of examples going back to Kontsevich and Quinn and many others. And the treatment that I'll be following when I describe these theories will be is described in a very nice paper by Freed, Hopkins, Lurie, and Telemann from some time ago. So to define one of these finite homotopy theories, we start with the data of a pi finite space. This is a topological space, just defined really up to homotopy type. It's a topological space which has finitely many connected components, each connected component has finitely many non-zero homotopy groups, and each of those homotopy groups is a finite group. And if you look at these such spaces, the connected components of one of these spaces, then they're all built out of what are called Eilenberg-MacLane spaces. So K pi Q is a topological space defined up to homotopy type, which has only one non-zero homotopy group. It's in degree Q, and that homotopy group is the group pi. So we can build all finite homotopy pi finite spaces by iterated fiber products of these Eilenberg-MacLane spaces. So for example, if I consider G a finite group, then KG1 is known as BG, and that's the classifying space of G bundles. If I let Q be positive, then the group pi has to be abelian, so I write it capital A. And these Eilenberg-MacLane spaces, if I consider the finite homotopy theories for such Eilenberg-MacLane spaces, these are the theories that we would use to describe what's called Q-form symmetry for groups A. And then, as I said, we can take fiber products of an Eilenberg-MacLane space over another one. And if we take a KA2 over BG, that's what's called a classifying space of a two group. And it's used to describe what some people call two group symmetry. So in general, these pi finite spaces are also known as higher groups. So what we'd like to do is we'd like to define a p-dimensional topological field theory, sigma xp, where the dynamical fields are, at least notionally, maps to X considered up to homotopy. I said we're doing fields without fields, but now in order to describe these, I'm going to describe the dynamical fields. In some sense, we integrate over the dynamical fields. Those are going to be finite sums in this finite homotopy world. Okay, so in order to specify the theory, however, we also have to specify the codomain. And that's usually glossed over, so I'm going to stress that a bit. So the topological field theory should really be denoted sigma p sub xc. In our paper, it's written sigma sub p sub x. Now, just to stress this point, let's review two constructions from category theory that change the category number of a monoidal n category C. So you can go down in category number. It's called looping. So because it's a monoidal category, it has a monoidal unit, which is called 1C. And so we can consider the Hom space of 1C to itself. Remember, in an n category, the Hom space between objects is an n-1 category. So this hum space from the unit to itself is a monoidal n-1 category. And once you've opened this possibility of going down in categorical number by looping, you can keep going down. And if we iterate the looping operation n-1 times on our category C, we get a 1 category. And in our paper, we always take that 1 category to be the category of finite dimensional vector spaces, complex vector spaces. Once we've done that, then we're obliged to take the nth looping to be 0 category, which is just a set, which is the complex numbers. On the other hand, in our paper, different choices of 2 categories are used in different examples. So in some examples, we take the 2 category from looping n-2 times to be the 2 category of categories I described before. And in other examples, we take the 2 category to be the 2 category of algebras in vector spaces. The latter choice is quite nice because it leads to a language of modules over an algebra. And at the end of the talk, I'll be coming to that. So just to really stress this point, if I look at a 2-dimensional gauge theory for a finite group G, and I choose my codomain to be the 2 category of categories, then the value of the field theory on a point would be a category, which is you get good results if you take that category to be the representation category of G. Or if the 2 category is the 2 category of algebras and vector spaces, then the value on a point will be an algebra, and you get good results if you take that algebra to be the group algebra of the group G. Because of something called the cobordism hypothesis, if you know the value of your field theory on a point, then really everything else is determined. But anyway, so this stresses that the results really depend on the choice of your codomain category. Now, I said there were 2 constructions in category theory. The other one is going up in category number. So you see, if you have a monoidal category, an n category, a monoidal n category, then there's a notion of an algebra object. So an algebra object X would be an object with a morphism from X tensor X to X. And that's the generalization of the idea of an algebra. That's an algebra object. And if we consider the set of such algebra objects, they are 0 morphisms, are objects in a n+1 category, which I'll call the Morita category. So you can go up in category number by this Morita construction. And in fact, we've already used this construction when I talked about algebras and vector spaces. Those were the algebra objects in the 1 category of vector spaces. And that's the 2 category of algebras, bimodules, and bimodule maps. But then this generalizes if we take the 2 category of categories. What is an algebra object? It's a category C with a morphism from C tensor C to C. That makes it a tensor category. And so we have the 3 category of tensor categories. So the 0 morphisms are tensor categories. And we have bimodule categories of the 1 morphisms, bimodule functors, 2 morphisms, natural transformations of such bimodule functors of 3 morphisms. So now choose a monoidal P category as your codimension, as your codomain. And then what in these finite homotopy theories, the value of the theory on a k-dimensional compact manifold without boundary will be an object in the kth looping of the P category C. And that's going to be true for k going from 0 to P. So now I'll say something about what something concrete about what those values are for the highest dimension, lowest codimension. So k is P, P-1, P-2, and P-3. It's actually good to start with codimension 1. So to describe that, I need a notation for any manifold M of any dimension. I'll let x to the m denote the set of continuous maps from M to X. And then with a compact open topology, that is itself a topological space. So just to reiterate what I said on the previous slide, the value of our field theory on a P-1 compact manifold without boundary will be an object in the P-1 looping of C, which we agreed will be the 1 category of vector spaces. In other words, the value on MP minus 1 will be a vector space. It's called the space of states on the spatial slice, M sub P minus 1. Just as an aside, I put space of states in quotes because vectors which are determined by abordism from the empty set to a spatial slice might very well be 0. And so they're not actually states in the sense of quantum theory. So people who apply quantum information theory, who apply topological field theory in the context of quantum information theory need to bear that in mind. Okay, so now I'm going to write down an explicit formula for what is this space of states once I'm given the data of X and C. Now, before doing that, it's good to recall the textbook field theory description of spaces of states and scalar field theories on sigma models. So what is this X to the M? It's the space of maps from M to X. And what is that? That's just the space of scalar field configurations in a sigma model with space-time M and target space X. And in textbook scalar field theory, we would put a Riemannian metric on M and on X, and then the states would be described by normalizable wave functionals of the field configurations. So a physicist would typically write that as capital psi for the wave functional evaluated on some field configuration, phi of X. So phi is in this mapping space, X to the M. And then because of these Riemannian metrics, we have a measure on the functions on X to the M, and we can talk about normalizable functions. And our Hilbert space of states is L2 of X to the M. So that's what you see in the textbooks on quantum field theory. Now, we're in this homotopical world, in this topological field theory world. We just work up to homotopy equivalence. So instead of normalizable functions on our mapping space, we talk about locally constant functions on our mapping space, X to the M, MP minus 1. MP minus 1 is the spatial slice. Now, what is a locally constant function on a topological space? Well, a locally constant function on a topological space must be constant on each connected component. In other words, a locally constant function on a topological space is nothing other than a function on the set of connected components. So here's the official definition of the finite the state space of a finite homotopy theory with target space X. It's the vector space of functions on the set of connected components of the mapping space X to the M. Here's the definition again. So for example, if I took X to be the Eilenberg-MacLane space for a abelian group A in degree Q, then basically by the definition of an Eilenberg-MacLane space, the set of connected components of the mapping space is the Qth cohomology of our spatial slice with coefficients in A. If X is K of G1, then the set of connected components of the mapping space is the same thing as the set of isomorphism classes of principal G bundles over the manifold MP minus 1. So then our state space is the vector space of functions of G bundles over the spatial manifold, MP minus 1. So what we've done is we've replaced this mapping space, X to the M, by something linear, a vector space. And in the paper and elsewhere in the literature, that's called the quantization of the mapping space, X to the M. I'll come back to this terminology. Okay, now we know what the state spaces are. Now, how about the quantum amplitudes from an initial state space on some initial spatial manifold N0 to the final state space on some final spatial manifold N1? Well, to describe this, we need to take a little correspondence course. So what's a correspondence? A correspondence, quite generally, is simply a collection of three sets, S, R1, and R2, and mappings F1 and F2 from S to R1 and R2, respectively. And this generalizes the notion of a function from R1 to R2. If I had a function from R1 to R2, the correspondence I would write would be the graph of the function. Now, we know that we can compose functions, so we would like to compose correspondences. So if we have two correspondences, we'd like to define a notion of how they compose to give another correspondence like that, where the diagram commutes. So in the world of homotopy theory, you can do that in a very nice way using something called the homotopy fiber product. So if S1 and S2 and B are topological spaces, and F1 and F2 are continuous maps, then we can define what's called the homotopy fiber product. And by definition, it's the set of triples of a point in big S1, another point in big S2, and a homotopy, a path in B from the image of S1 to the image of S2. And we include that gamma, that homotopy, as part of the data of points in the homotopy fiber product. So it's very big. It includes all these paths. But it has good properties. So if we have two correspondences of topological spaces, then you see in the middle here, we have exactly the kind of data you need to define a homotopy fiber product. So you do that, and that's your new correspondence. And this way of composing correspondences gives a composition with good properties as one learns in courses on homotopy theory. And it's just what we need in our case. So going back to the description of amplitudes from an initial to final spatial slice, if we have a Bordism, then we have a correspondence of mapping spaces. So remember, X to the MP is the space of maps from the Bordism, MP, to the target space X. And we could restrict those maps to the initial and the final spatial manifolds. And so that gives you maps R0 and R1, defining a correspondence like this. So our idea is we'll define the linear transformation on mapping spaces by a pullback and push forward construction. The pullback and push forward on functions, on the connected, locally constant functions. And the pullback is straightforward. The push forward is not so straightforward. If I have a locally constant function on X to the MP, then using this map R1, I want to produce a push forward function, which will also be locally constant on the mapping space X to the N1. And the formula is this. So the value of this push forward function on some mapping, H, is, well, I take H, I look at its inverse image under R1. That's some subset of X to the M. It has connected components. For each connected component, I choose a representative and I evaluate psi on that representative. Since psi is locally constant, it doesn't matter which one I choose. And I weight it by this alternating product of the orders of these homotopy groups. This is called the homotopy cardinality. And so now this formula has good properties so that the amplitudes now compose properly as they should in field theory. And that follows from properties of the homotopy fiber product and from the homotopy cardinality. Excuse me. So now, if I want the partition function, I would just choose the initial and final spatial manifolds to be the empty set. So now let's go on to codimension 2. So as I said, we have to choose what is our codomain, and let's choose for definiteness our codomain so that the P-2 looping is the 2 category of categories. So the value of our field theory on a P-2 dimensional manifold with a boundary must be a category. And it should be some kind of locally constant vector spaces over this mapping space. And you can make that quite precise. You take what's called the fundamental groupoid of the mapping space, and you take the vector bundles on that fundamental groupoid, and that's a way of formalizing the notion of flat vector bundles over the mapping space. And again, this is some kind of linear object, which we call the quantization of the mapping space X to the MP. So for example, if X is BG and we're doing finite group gauge theory, then this fundamental groupoid is the groupoid of principal G bundles over our manifold. And so we would be talking about the locally constant vector bundles over the groupoid of principal G bundles. Finally, I'll even give you the answer for codimension 3, where I'll specialize to a Morita category, the 3 category of tensor categories, and I'll choose our dimension to be P equals 3. So then, and I'll take my target space to be BG, so we're just talking about G gauge theory. Then the value of this 3-dimensional gauge theory on a point is the tensor category of vector bundles on the group G. So to make the tensor product structure is a convolution formula that looks like this. So this defines a tensor product on vector bundles over G. Okay, so at each categorical level, we see some kind of quantization of suitable correspondences of mapping spaces. This is not quantization in the terms of symplectic geometry, but in the homotopical sense that I've been describing. A precise formulation of this notion of quantization in this setting is given to some extent in the paper of Fried, Hopkins, Lurie, and Telemann, section 8.4. But I think if you look at it, you'll agree with me that there's actually some room for a more thorough exposition. But be that as it may, we have some notion, I hope, of what these finite homotopy theories give you. Now, there's a piece of data in finite homotopy theories that I've been suppressing until now, which is in addition to the choice of X and codomain C, we can also consider a twisted construction where we make a choice of a cocycle, a P cocycle, on X with values in C star. So if X is BG and we're doing G gauge theory, these would be Dykgraaf-Witten theories. So really, the full set of data that defines a finite homotopy theory is a set X, C, and lambda. And so how does this lambda change the answers? Well, it modifies them only slightly. So for example, if I were to describe the state space on a P-1 dimensional compact manifold without boundary, well, what I would do is instead of locally constant functions, I would consider the vector space of locally constant sections of a flat line bundle over the mapping space, where I would construct that flat line bundle, L lambda, by using the data of the cocycle, the twisting. Okay, so now one thing we do in our paper pretty extensively is talk about defects in domain walls and boundary theories. And so what we claim is that we can extend this Fried, Hopkins, Lurie, Telemann description of these finite homotopy theories to a general theory of defects in these theories. And that in turn suggests a general framework for describing defects in general topological field theories. Now, defects are associated to subsets of space-time, Z, where Z need not be smooth. It might be something like this picture here. And now, what would we like to know about these defects? Well, we'd like to know, how do we even go about describing them? So what kind of data do we need to give in order to specify uniquely a defect? Or more informally, what are the labels carried by a defect? Well, that turns out to be actually a fairly complicated question. There are classical labels, there are semi-classical labels, global labels, and local labels. I'll say something about these. Then once we know how to describe a defect, the next thing we would want to know is how does the presence of such defects affect the quantum values of these theories on various manifolds? So let D of Z be one of these defects. So if we have a manifold and a defect, how is the partition function, the state space, and so on affected? Now, sometimes there's a product law on defects, and we would like to know how to describe this product law. So let me begin with the classical labels. So let's assume for this that the classical label, that Z is a smooth manifold of codimension L. So it's a nice smooth manifold of codimension L. And then around any point on Z, there's a linking sphere. So transverse to this defect is living on Z. It's codimension L. So transverse to the defect is an L-dimensional disk pictured in maroon here. And the boundary of that disk is an L-1 sphere, which is called the linking sphere. And so the most natural thing you might think of is, well, we'll just study the topology of the bulk fields on the linking sphere. So the classical labels would be something like choose a connected component of the mapping space of the linking sphere to the target space X. And Those are classical labels. And although it's commonly used in the literature, they can in fact be inaccurate for describing quantum systems. And we give examples of that in our paper. So let's explore what other labels we might want to use when describing defects. Well, one thing is what we call global labels. So here we would surround Z by a small neighborhood. Small, we're doing topological field theory. What do I mean by small? Small means that the neighborhood doesn't intersect any other defect. So we would surround Z by a small neighborhood, U sub Z, which has a nice smooth manifold boundary, boundary of U sub Z, like in the picture. So then the boundary of U sub Z is a codimension one smooth manifold. So there's an associated state space. This is a very physical thing to do. You surround your defect, you ask what state is induced in the theory on the boundary of the neighborhood surrounding the defect. That's the global label. So it's an element of the state space on the boundary of this neighborhood. Because it's topological, all I have to do is say that this neighborhood doesn't intersect any other defects. So it's a vector in a complex vector state, vector space, the state space of this neighborhood. That's the global label. But you might, this might be very hard to get your hands on. You might want to say, well, can we look more locally on the defect and describe it that way? And those are the local labels. So when Z is a smooth submanifold, we can hope to characterize our defect by examining just the neighborhood of a point of the defect. And so the basic idea here is to try and implement Kaluza-Klein reduction along the linking sphere of that point. Remember, L is the codimension. And so if you follow that idea through, then the local label is a little complicated. Let me unpack this formula for you. So the value of our field theory, of our p-dimensional field theory on a linking sphere is what? It's an object in some higher category. What higher category? The L-1th looping of the category C. Now, there's also the unit in that L-1 looping of C. And so we can consider the Hom space from the unit to the value of the field theory on the linking sphere. Now, that Hom space, remember, is a higher category. It's an M minus L minus 1, which is an M minus L category. So the local label is an object in an M minus L category. Okay, so now probably your eyes are crossing. If they haven't been crossing before, your eyes are crossing now. So let's do a sanity check. Let's just take the codimension to be the same as the dimension of space-time. In other words, let's take a point defect. So then we'd better find that our local label is a global label. Okay, well, if we take L as P, then the P minus 1th looping of C, we agree, is the one category of vector spaces. And the unit, I said, in the one category of vector spaces is the one-dimensional complex vector space. So, and the value of the field theory on SP minus 1, we already discussed, is the vector space of states on the sphere. So what is something in Hom from C to that vector space? It's a vector in that vector space. So the global label, the local label, is a vector in the state space on the sphere. And that's well known to physicists. It's called the state operator correspondence. So, okay, so things are working well there. Now, as we go to higher dimensional objects, that is lower codimension, then there's a real difference between local and global labels. And what we claim in the paper is that if Z is smooth with trivialized normal bundle, then the local label actually does determine the global label. And that's it's basically the Kaluza-Klein idea, but it's also, I want to be careful about my time and I'm running low, so I'm going to skip that discussion. Suffice it to say that you can show that. Now, if you don't have a trivial normal bundle and if Z is not a manifold, then it all gets very complicated. And just to impress upon you that it's complicated, here's a diagram which was drawn by Dan and Constantine in the context of our discussions, and actually teched by my son, Andrew Moore, with some touch-ups by Dan, just teching this thing is non-trivial. So this is just to impress upon you that it's a non-trivial story in the general case. Now, one key point you get from the general theory of defects is the following. When Z is not smooth, we treat it as a stratified space, and we consider the links where we start from the lowest codimension, the highest dimension up, the lowest codimension, and then we move up in codimension, looking at the more singular parts of Z. Okay, now that's just an abstract discussion of where labels should live. Can we actually compute labels? Well, the point about these finite homotopy theories is they're very computable. So if we have one of these finite homotopy theories determined by some target space X, we can actually compute the local and global labels from what we call semi-classical data. And you should think of the semi-classical data as dynamical fields for the defect. So the definition of a semi-classical local defect data is some topological space Y and some continuous map psi from Y to the mapping space X to the S to the L minus 1. And then we'll apply the quantization procedure of FHLT to a correspondence that looks like this. So again, let's try and do a sanity check with the point defect. So the codimension is all of the space-time dimension. We're talking about a point defect. The local label, as we discussed, should be an element of the Hom from C to the state space, which is a vector in the state space. And we agreed before that the state space is the locally constant functions on the mapping space X to the S to the P minus 1. So the point is that we, given this defect data, a space Y and a map psi, we can compute this vector in the state space. It's going to be the quantization of this correspondence. So if we pull back from a point, we're going to get a constant function on Y. Might as well take that constant function to be the function 1 on Y. And then what's the push forward under psi? Well, the push forward under psi is the same kind of formula with a finite sum weighted by homotopy cardinality. So what's the value on one of the connected components? Well, if H is in the mapping space, to evaluate the push forward function on H, we would look at the inverse image of H under psi. It's a set with some connected components. We evaluate the function 1 on that representative, that's of course 1, and we weight it by the homotopy cardinality. So the point is not so much the specific formula. The point is that I can compute. I can, given the semi-classical defect data in green, I can actually compute the local label, which in this case is the global label. How will we go about computing the values of the amplitudes, the state spaces, the partition functions, everything in the presence of a defect? Well, we would introduce mapping spaces of pairs. We would have a bulk field. We already had the bulk field as our notional dynamical field in the finite homotopy theory. So it's a map from whatever space-time we're looking at to the target space X. And another field, the defect field, from Z, the domain of our defect, to this space Y. Now, we already had the defect data defining the defect data, which is a map from Y to the mapping space of X to the linking sphere. And so we require that this pair of maps, bulk and defect maps, be compatible with that data. So they have to make this diagram commute. So now we have some mapping space, calligraphic M, which is simply the set of these pairs satisfying this constraint. And then quantization, in the sense of this homotopy quantization that I described before, will give you the partition functions, the state spaces, the amplitudes, and so on, of the theory in the presence of the defect defined by the data psi and Y. Okay, so that's how you compute. Now, if we specialize to codimension 1, then we are, of course, talking about domain walls between the theory and itself. Once we do that, of course, there's a natural generalization where we can have different finite homotopy theories on either side of the domain wall. So we can take different spaces x1 and x2 on either side of the domain wall. Why not? So then it's easy to implement the semi-classical data that defines such domain walls between different finite homotopy theories. And that would just be a pair of maps from Y, it's a common space Y, to the different target spaces x1 and x2. And now we can describe boundary theories by taking the target space on the left to be the empty set, or the target space on the right to be the empty set, depending on whether we want our boundary on the left or the right. Now, in the context of these finite homotopy theories, there are two very canonical boundary theories we could talk about. We could choose Y to be a point. So then what is psi? Psi is a map from a point into X, considered up to homotopy. So psi just chooses a connected component of X. Those we call Dirichlet boundary theories. And then another canonical thing we could do is we could take Y to be X itself and demand that psi be homotopic to the identity. Those we call Neumann boundary theories. And those are good names, because if we specialize to our target space X as BG, in other words, doing G gauge theory, then these, if you work it out, these really are Dirichlet and Neumann boundary conditions for gauge theory. But now, lots of other boundary theories are possible. So, for example, sticking with BG, there's the general set of semi-classical boundary theories. I said conditions. It's really better to think of them as boundary theories. Is given by the data of a homomorphism from H to G. So given a homomorphism from H to G, my space Y in my semi-classical defect data would be Y is BH, and psi is the induced map from the homomorphism F of BF. Now, if I include a twisting by lambda, in other words, if I'm describing p-dimensional Dicroft-Witten theory, then I need to include some extra data of a cochain that trivializes the pullback of lambda. And so now if I have a space-time with a spatial manifold n, then the relevant mapping space is, again, spaces of pairs that satisfy this consistency condition. And if you sit down and think about what this consistency condition is saying, it's just saying the very, very natural thing in gauge theory, that on the boundary, you're reducing the structure group of the boundary from G bundles to H bundles. And if you work out what this is saying about the degrees of freedom on the boundary, you're just getting a homotopical sigma model of maps from the boundary n to the coset space G mod f of h, which is exactly what you expect when you have spontaneous symmetry breaking from G symmetry to H symmetry. So it really makes a lot of sense. And here's a simple example of a quantum result with boundary conditions like this. I'll take a three-dimensional gauge theory. I'll choose my codomain theory to be algebras in the two category of categories. In other words, the three category of tensor categories. And let's consider the value of this theory on a morphism from the empty set to a point where we put the boundary theory determined by f and mu on one side. So so this is a morphism from the empty set to a point. So it's an element in the Hom space in the Morita category from the unit to the value of sigma 3 on a point. Well, I said before that sigma 3 on a point is the tensor category of vector bundles on G. And then a theorem in math says that the general module for that module category for that is vector bundles on G mod H. And the module structure is described by this kind of formula, a kind of convolution formula again, where if there's a cocycle around and we're doing Dicroft-Witten theory, we twist by some line bundle constructed by the cocycle lambda. And you can go on and describe defects within defects. And we use that in the paper to describe the composition of domain walls that separate Neumann boundary theories from Dirichlet boundary theories and vice versa, and how they multiply. Now, I said before that classical labels are inadequate, and I'm running out of time, so I won't go through this, but we have very explicit examples in the paper where the classical labels give you completely the wrong picture for how to label defects. So I've only got 10 minutes left, so I do want to get to one of the main points of our paper. And that is a picture of how these finite homotopy theories implement symmetries, internal symmetries with Q-form finite group symmetries and generalizations thereof. So there's been a lot of talk in the past few years about generalizations of symmetries and the notion of symmetry. And you hear things about generalized and categorical and non-invertible and adjectives like that, symmetries. And so we described a framework for understanding what these terms could mean using what we call the sandwich, or we prefer to call it the quiche picture. And there are two motivations for this quiche picture. One motivation is if we consider our codomain category to be a kind of Morita category, then there's a strong analogy between a topological field theory and an algebra, and it's more than an analogy in some cases. So if we take finite homotopy theory with BG as our target, then in 2 dimensions, the value on a point is an algebra, it's the group algebra of G. And in 3 dimensions, it's the tensor category of vector bundles on G, which is an algebra object in categories. And then the boundary theories would be modules for the algebra. And then you can import notions from algebra, like the notion of a regular representation. And an important idea in abstract algebra theory is that it's good to separate the notion of an abstract group or an abstract algebra from its action on a particular module, because then relations between algebra elements will be universally true in all modules. So when you translate that idea to the field theory context, what you end up realizing is that you can compute relations among defects in non-topological theories by doing computations within a topological field theory. So that's one motivation. Another motivation is a very concrete example. Consider 4-dimensional Yang-Mills theory for a compact group SUN. Now, famously, from the Lagrangian, we cannot tell if the gauge group is G or the adjoint group PSUN, or maybe G mod A, where A is some subgroup of the center of G, the center of G being Zn in this case. So let's let F denote the 4D G gauge theory. And when we calculate the partition function or the Hilbert space of SUN gauge theory, we're instructed to sum over all principal G bundles. Now, in 4 dimensions, the isomorphism class of a principal G bundle is just determined by its second Chern class. But contrast that with PSUN gauge theory, where to compute the partition function or the Hilbert space, we have to sum over all G adjoint PSUN bundles. So the isomorphism class in 4D of such bundles is determined by a second Chern class and a 't Hooft flux in physics, or a Stiefel-Whitney class, which is an element of the second cohomology of M with values in Zn. Now, remember that these Eilenberg-MacLane spaces are designed so that the set of connected components of the mapping space X to the M, where X is this Eilenberg-MacLane space, is that cohomology group. So we can think of W2 of P this way. And so what I'm saying is that the gauge bundle of the PSUN gauge theory really determines a topological Zn gerb on the 4-manifold. And that suggests that the 4D PSUN gauge theory should be a boundary theory for a 5-dimensional finite homotopy theory with this target space X, which is this Eilenberg-MacLane space. And that's almost true. So we can couple a theory F tilde on the boundary of this finite homotopy theory, 5-dimensional finite homotopy theory, on M5, which is your 4-manifold times, say, the negative real line, by demanding that the boundary value of the bulk gerb is homotopic to the gerb described by a PSUN bundle. So F tilde is almost a PSUN gauge theory, but it has an extra field, which is this isomorphism, an extra topological field, which is the isomorphism of the boundary value of the bulk gerb with the gauge theory gerb. So now let's include a topological boundary theory for the finite homotopy theory on the left, call it rho. Well, the important thing is that because sigma 5 is a topological theory, we can squish that interval down. And so the picture that you're looking at is really a picture of a four-dimensional gauge theory. And it's a four-dimensional gauge theory with the gauge algebra SUN. And then we can get different gauge theories by choosing different boundary theories rho. So for example, if I choose the Dirichlet boundary condition, then that trivializes the gerb. So then, because the interval's topologically trivial, that means I've trivialized the bulk gerb in 5 dimensions, which forces us to trivialize the gerb on the space-time on the right. And so that means that we couple our Yang-Mills theory only to the PSUN bundles with trivial gerb. Those are SUN bundles. So this is SUN gauge theory. On the other hand, if I put a Neumann boundary condition on the left, then I get a PSUN gauge theory because there's no constraint on the gerb. I have to sum over all PSUN gauge bundles. And then there's other boundary conditions, boundary theories, as I stressed before. These finite homotopy theories have lots of different boundary theories. So I don't have time to go into those kinds of details. But I want to finish then with a definition, 2 key definitions on our paper. So the first definition is a p-dimensional quiche is a pair, rho and sigma, where sigma is a p plus 1 dimensional topological field theory, and rho is a p-dimensional topological boundary theory. In the algebra language, you can consider it a right module for sigma. And then definition 2 is that an action by the quiche, rho sigma, on a p-dimensional field theory F, not necessarily topological, is a boundary theory, thought of as a left module for sigma, call it F tilde, not necessarily topological, and an isomorphism of this p-dimensional theory with our p-dimensional theory F. So that isomorphism is called theta. So that's the data that we give. That's the data we use to describe an action of the quiche on a p-dimensional field theory. Now, notice, by the way, that if I fix the data of rho, sigma, and F tilde, and I choose different thetas, what do they differ by? They differ by an automorphism, an element of the automorphism group of F, which is the traditional notion of what a symmetry is. So this partially justifies, in my mind, the viewpoint that this is a symmetry. Okay, so I'm out of time. We have lots of examples. We also describe how to multiply these defects. Don't have time for that. So let me conclude with some open problems. In the paper, as I've mentioned, there are several examples of topological subtleties and labeling defects and the composition laws of defects. It would be nice to see some more physical consequences of that. And in the same vein, we describe some applications to duality defects and modular invariant combinations of left and right movers in 2D CFT. It'd be nice to see more physical applications. A question I find interesting is would it be possible to describe these finite homotopy theories in more traditional field theoretic terms, like BF theories or combinations of BF theories? Or could we describe, if I prescribe for you a finite homotopy theory and a topological boundary theory rho, could I invent a more traditional field theory with, scalar, the usual notion of scalar fields and gauge fields and maybe P-form fields and so on which this quiche acts? So for example, Dumitrescu, Introligator, and Cordova, went to some trouble to give examples of traditional field theories on which a 2-group acts. It would be nice to look at families of quantum field theories and maybe say something about higher Berry curvatures. And so far, all the symmetries we've been talking about really are internal symmetries. So it'd be nice to include how to include space-time symmetries in this framework. And I think we should start with parity and time reversal symmetries, because those are discrete symmetries, discrete space-time symmetries. And that raises the most important open issue for this picture, which is, what do we do about continuous symmetries? Can we incorporate continuous symmetries in this kind of framework for describing symmetries? So exactly at 1 hour, and so I will stop there, take questions.
Thank you.